So we started today morning with the principle of equipartition energy. So when we taught today morning, the voice was not clear. So I repeat the things what we discussed today morning, and then we are going to a new concept called the deviation of the behavior of gases from ideal nature. So that is what we are going to see today. See the principle of equipartition energy. Actually, the total energy of a molecule is divided equally among the different degrees of freedom of the molecule. What is actually degrees of freedom? We have seen in the previous classes. See, a molecule can possess energies in three different kinetic motions. One is called a translation motion, that is the movement of the entire molecule. Second one is the rotation motion. Third one is the vibrational motion. So each component of a kinetic motion contributes equally to the total kinetic energy, and that the kinetic energy for each degree of freedom is half kT per molecule or half RT per mole. This K is Boltzmann's constant. So this is per molecule. If you multiply this with Avogadro number, the K multiplied by Avogadro number will give you gas constant R. Therefore, 1 by 2 RT is per molecule. So each mode contributes an amount of half kT of energy per molecule. So if you take the translation motion means simply as a whole molecule moving here and there. It is called a translation motion. So the translation motion can be resolved into motion in three different axes. So along the x-axis, half kT, along the y-axis, half kT, along the z-axis, half kT. So totally 3 by 2 kT is the contribution by the translational motion. For rotational motion, if it is a linear molecule, I have already told you the multi-atomic molecule or the molecules having more than 2 atoms, they can be either linear or non-linear. If it is a linear molecule like a carbon dioxide, then the molecular axis cannot be treated as a rotational axis because about that axis, the rotation needs only negligible energy, or the moment of inertia about that axis is almost zero. Hence, that rotation is completely neglected. So the rotation in the other two perpendicular axes were considered. So it is only 2 degrees of two rotational degrees of freedom. So for linear molecules, the rotational energy contribution will be 2 into half kT. So each mode half kT, there are 2 modes. So 2 into half kT. For non-linear molecules, the rotation about all the 3 perpendicular axes will have an appreciable energy. Hence it is 3 into half kT for the non-linear molecules. If a molecule is having translational, rotational and vibrational motion, the vibrational motion, each vibrational motion can have 2 modes of energy. One is called the potential energy and the other one is called the kinetic energy. See, this is something like a stretching and compressing a spring. When the spring is stretched, the energy is stored in the spring in the form of a potential energy. When it is left free, the potential energy slowly drops down and the kinetic energy increases. And about the equilibrium position, the energy is totally kinetic. So there is a continuous interchange of potential and kinetic energies. So the potential energy contribution is half kT and the kinetic energy contribution is also half kT. So totally each mode of vibration contributes an amount of kT to the total energy of the system. So this is how the translational, rotational and vibrational energies are contributing to the total energy of the system. Now look here, suppose I am taking a gas, it has N1 number of translational degrees of freedom, N2 number of rotational degrees of freedom, and N3 number of vibrational degrees of freedom. So what will be the total energy of the system? N1 into half kT, this is for the translational energy. N2 into half kT, this is for the rotational energy. N3 into kT, because each mode has a kT contribution, whereas here each mode has half kT contribution. Here it has a kT contribution. Why kT contribution? Each mode in turn has two more contributions, namely potential energy contribution and kinetic energy contribution. Say for example, you take a hydrogen molecule, which is a linear molecule. So it has three translational motions and two rotational motions, because the rotation about the molecular axis is neglected. So two rotational motions, and then vibrational motion according to the formula which is previously discussed, number of atoms into 3 minus translational and rotational degrees of freedom. So total number of atoms 2, 3 into 2 6, 6 minus 3 plus 2 5. So totally 1 vibration. So the energy of translational 3 into half T, energy of rotational 2 into half T, there is only one vibration, so kT. So total energy is 7/2 kT per molecule. For water molecule, there are three translational motions. Rotation also three, because water is a non-linear molecule. So vibrational motion 3n minus 6. What is the 6? 6 is the combination of translation and rotation, where this 3 is the number of atoms. So 3n is the total degrees of freedom, minus 6, so you are getting 3. So water has 3 normal modes of vibration. I have already discussed what is normal mode of vibration. Normal mode of vibration means each bond should vibrate with equal energy and all the atoms should cross the equilibrium positions simultaneously. This is called normal mode vibration. So it has 3 normal modes of vibration. So the total energy can be calculated like 3 into half kT for translation, 3 into half kT for rotation, and 3 into kT for vibration, totally 6 kT per molecule. Similarly, if you take carbon dioxide molecule, the difference between carbon dioxide molecule and water molecule is water is non-linear and the carbon dioxide is linear, but the total number of atoms in both is the same. For water also it is 3, for carbon dioxide also it is 3. But you look at the energy, for the translation it is 3, for rotation only 2, because the rotation about the molecular axis is neglected. So vibration, it becomes a 4. So 3 into 3 minus the sum of translational degrees and the rotational degrees 5. So 9 minus 4, 5, 4. So total energy is 3 into half kT for translation, 2 into half kT for rotation, and then 4 kT for vibration. So totally 13/2 kT per molecule. So this is how the total energy of the system is calculated. Now you look here, we want to discuss the heat capacity of the ideal gases. You might be knowing what is heat capacity. Heat capacity is the total quantity of heat energy required to rise the temperature of a body by 1 degree. What is specific heat capacity? It is the quantity of the heat energy required to rise a body of mass 1 gram by 1 degree. What is molar heat capacity? It is the total quantity of heat energy required to rise the temperature of 1 mole of a substance by 1 degree. So these are all various definitions for heat capacities. So we have thoroughly studied the heat capacity in the second year thermodynamics, where heat capacity for the gases can be measured in two different conditions, namely at a constant volume and at a constant pressure. When it is measured at a constant volume, it is CV. When it is measured at a constant pressure, it is CP. You might have known this. CV is dou U by dou T. That is a change in the internal pressure. It is CV. But CP is dou H by dou T. The change in the internal pressure and the P into V. So what is the work done by the system during expansion, and also what is the change in the internal energy? The change in the internal energy alone with the temperature will give you heat capacity at a constant volume. But the change in the internal energy and also the work done by the gas will give you the change in the heat capacity. It is the heat capacity at a constant pressure. Now you see, before going to the heat capacity of the ideal gas, you should understand what is Born-Oppenheimer approximation. So Born-Oppenheimer approximation says that the total energy of the system is the sum of the energies possessed by virtue of translation, rotation, vibration, and electronic. So these are all the four different components. What is the energy possessed by the molecule by virtue of its translation motion? The energy possessed by the molecule by virtue of its rotational motion, the energy possessed by the molecule by virtue of its vibrational motion, energy possessed by virtue of the electronic setup. See, when you compare these energies, the highest is the electronic energy. Next to that, lower than that, vibrational energy. Lower than that, rotational energy. And the least among them is the translational energy. Normally, the rotational energy changes are observed in the microwave region, and the vibrational energy changes are observed in the infrared region, and the electronic energy changes are observed in the visible or ultraviolet region. So, and the spectra, corresponding spectra, you might have studied in the spectroscopy also. The corresponding spectra, rotational spectra is observed in the microwave region, vibrational spectra is observed in the IR region, electronic spectra is observed in the visible or UV region. See, if you consider an atomic gas is the one which is stable in the atomic form itself. Say, for example, all the noble gases, helium, neon, argon, krypton, xenon, radon, they are all called atomic molecules because they are not combining with any more atoms to attain stability, because they themselves have completed octet and helium has completed a duplet. So they are stable as such. So they do not combine with one more atom to attain the stability. They are called atomic gases. See, these atomic gases can be considered as a single particle. When you take only one particle, the particle may have a translation motion. The rotational motion is completely neglected in all axes for a single particle. The reason is the moment of inertia in all the three axes for a single particle is almost negligible. And also, vibration is observed only when two or more atoms are bonded, because it is only the vibration of a bond. But a single particle does not have bond with any other particle. Therefore, the rotational degrees of freedom and the vibrational degrees of freedom for an atomic gas are completely neglected. Hence, the atomic gases which are considered as single particles will have only translation motion. So, but each translation contributes an amount of half kT to the total system. Therefore, the total energy of an atomic gas is 3 by 2 kT due to the three translational motions in all the three axes. This is the statement of Clausius. So what Clausius states is that the total energy of the atomic gases is only the translational energy, which is equal to 3 by 2 kT. And this 3 by 2 kT is 3 into half kT, that is the translational motion in three different axes. Suppose if the atomicity is n, that is atomicity is higher than 2, then what will happen? You have to check whether the molecule is linear or non-linear. If it is linear, the vibrational motion is 3n minus 5. Non-linear, the vibrational degrees of freedom is 3n minus 6. So having this fundamental understanding, you may calculate the heat capacity at a constant volume is equal to dou E by dou T at a constant volume. So the CV total, the total heat capacity at a constant volume is translational heat capacity, rotational heat capacity, and vibrational heat capacity. They are all summed up. Normally, we do not take electronic heat capacity because its energy gap is very high. So each degrees of freedom is contributing half kT, and each vibrational degrees of freedom is contributing kT. Now you have to understand one particular point. By definition, heat capacity is the quantity of heat energy required to rise the temperature of a body by 1 degree. This 1 degree difference can be taken at any temperature. Suppose you are taking a gas and the temperature of the gas is minus 100 degrees centigrade. You want to rise the temperature by 1 degree. Now you are raising the temperature of the system to 99 degree. There is 1 degree temperature change, and you are trying to calculate the quantity of the heat energy supplied. Suppose the same gas is kept at 1000 degrees centigrade and you are raising the temperature by 1 degree. That is, you are raising the temperature so that the system will reach a temperature of 1001 degree. Now you measure the heat energy spent. These two heat energies are not equal. This is because the vibrational contribution is frozen at lower temperatures. This is the understanding. So at room temperatures, the vibrational contribution, the contribution to the total heat capacity by the vibrational motion is only about 20%. When temperature goes down, it further goes down. And when the temperature is very low, it can be taken as if the vibrational contribution is completely frozen. But the vibrational contribution becomes predominant at only higher temperatures, which means that when temperature is brought down and down and down, vibrational motions are completely restricted. They are restricted. But when temperature goes up and up, the total energy, the contribution by the vibrational energy alone predominates. See, in quantum mechanics, you will be clearly studying this. There is a special problem called the heat capacity problem. How the classical mechanics was a failure and the quantum mechanics was successful in explaining heat capacity. That itself is a very big chapter in quantum mechanics. There this statement comes: at a lower temperature, the vibrational contributions are frozen. But at higher temperatures, the vibrational contributions predominate. But quantum mechanics also says that for vibrational motion, 0 point energy is there. You might have studied what is 0 point energy in spectroscopy. 0 point energy means even at 0 Kelvin, there is a small portion of vibrational motion. Because when vibration is at rest, there is no vibration at all. You are very sure about the momentum of the particle as 0. and also you are sure about the position of the particle, which is a violation to the Heisenberg's uncertainty principle. In order to avoid this violation, it is assumed that the vibrational contribution is there even at 0 Kelvin. But the vibrational contribution to the heat capacity is approximated to be frozen. There is an approximation. This is only an approximation. It is approximated that at low temperatures, the vibrational contribution is less, and at high temperatures, the vibrational contribution is predominating. So up to this point, we have discussed today morning. And now we are entering into a new topic in the gaseous state. We are going to approach the characteristics of the real gases. Look here, I have already told you the fundamental differences between real gases and ideal gases. Ideal gases do not have intermolecular interactions. They neither attract each other nor repel each other. That is the fundamental property of an ideal gas. Whereas the real gases show attraction. Having these characteristics in mind, we have related the pressure and the temperature, volume and the temperature, pressure and the volume, pressure and the number of moles. These are all related by Boyle's law, Charles' law, Gas-Lucas law. So these are all various laws by which these parameters have been interrelated. These interrelations have been summed up, and finally we could arrive at an equation which is PV is equal to nRT, which is called the ideal gas equation. This ideal gas equation is applicable only for ideal gases, which means the gases which do not have intermolecular interactions. But when you apply the same equation to the real gases are observed to obey the ideal gas equation at very low pressures and at high temperatures. Because at low pressures, the gas molecules are far apart. They go far away from each other and they are widely separated. And also at high temperature, the intermolecular interactions will vanish. They will get broken. Hence, at low pressure and at high temperature, even though they are real gases having the intermolecular interactions, they are far apart, they are too much separated to have intermolecular interactions. And the temperature is also high because the intermolecular bonds are broken. So real gases will behave as an ideal gas at low pressure and at high temperature. But at high pressure and low temperature, what will happen? The gas molecules will come closer, and the decrease in the temperature will favor the intermolecular interactions. Therefore, the deviation from the ideal behavior is found to be greater at high pressure and low temperature. And also, this high pressure and low temperature, this business, deviation is much more in the case of gases which are easily liquefiable and which are easily soluble in liquids. Say for example, carbon dioxide, sulfur dioxide, ammonia, these are all easily liquefiable gases. Liquefiable means it is not by the decrease in the temperature, it is by pressurization. If you take liquid ammonia and supply sufficient pressure, it will become a liquid. Similarly, sulfur dioxide, even you might have seen solid carbon dioxide. If you go to the ice cream parlor and if you ask for ice cream parcel, you will be given the parcel with the thermal insulative box, and inside the box the ice cubes will be kept around your ice cream pack. Actually, the ice cubes kept inside the parcel, it is not liquid ice, it is a dry ice. Dry ice means it is solid carbon dioxide. It will undergo only sublimation. The carbon dioxide in solid state will directly evaporate into gaseous state. So if you touch, it will be completely dry, but it is ice. It is called a dry ice. So formally, in the olden days, this dry ice was used to cause artificial rain. Say what they will do? They will take the dry ice in a helicopter and they will spray the dry ice over the cloud. Now the cloud will get cooled down and there will be condensation of the water molecules and artificially you can cause rain. But nowadays it is done with silver iodide or some silver compounds where the coagulation and the precipitation is favored. In olden days it was done with liquid carbon dioxide, solid carbon dioxide. So the carbon dioxide, sulfur dioxide, ammonia, they are all liquefiable gases or highly soluble gases. Why highly soluble gases? You can dissolve carbon dioxide in water, which is nothing but your soda water, your Pepsi, Coca-Cola, or any other carbonated drink. It is nothing but a carbon dioxide dissolved in water. This you can do even at home. Soda maker. There is a device called soda maker in which a carbon dioxide cylinder will be given. The prescribed bottle will be there. You fill water in the bottle and keep it inside. Simply press it 3 or 4 times. That's all. Your ordinary water will become soda. Similarly, sulfur dioxide can be dissolved in water. Ammonia can be dissolved in water. Even 1:1 ammonia is possible. 1 ml water, 1 ml ammonia will dissolve, which is called 1:1 ammonia or ammonium hydroxide. So for these gases, the deviation from the ideal behavior is very high. But for hydrogen, oxygen and nitrogen, the deviation is very small because they are not easily liquefiable. They are not easily soluble, but they are soluble. Oxygen is soluble in water. If oxygen is not dissolved, no fish will survive. Hydrogen and oxygen can be liquefied. The rocket fuels, liquid hydrogen, liquid oxygen, even liquid nitrogen is available, but they are not easily liquefied. Whereas carbon dioxide, sulfur dioxide, ammonia are easily liquefied. So in these cases, in order to make the difference between the ideal gas and the real gas, another factor is considered, which is called compressibility factor. What is this compressibility factor? PV of real gas divided by PV of ideal gas is called Z, the compressibility factor, which is equal to PV by nRT, because nRT is applicable only for ideal gas. So P into V by nRT. For an ideal gas, PV is equal to nRT means the numerator value and the denominator value are equal. Hence, Z will be 1 for ideal gases. Whereas, for real gases, it will not be 1. Look here, this is the graph where along the Z-axis, compressibility factor is taken. Along the Y-axis, atmosphere, that is the pressure is taken. For an ideal gas, it is 1. If this is the 1, it remains 1 for all pressures. But for real gases, you see here, ammonia, easily liquefiable. Z is much less than 1 and then it slowly rises and it becomes similar to ideal at a particular pressure and then it exceeds. For methane, the same trend is seen. For carbon monoxide, a same trend, but the shallow is less. It goes like this. But for helium and hydrogen, it is not going down at all. It becomes less than 1. It is always positive, but almost parallel to the ideal at our normal temperatures. So this is how the deviation is seen. Look here, high pressure and at low temperature. High pressure and low temperatures, molecules are very closer, hence the molecular repulsion will dominate. At low pressure, see, look here, carbon monoxide, methane, ammonia, for them Z is less than 1, which means attractive force is dominating. So when pressure is high, repulsive force dominates. When pressure is low, attractive force dominates. At a certain pressure, Z becomes greater than 1. But helium and hydrogen at all temperatures, Z is greater than 1. But below minus 165 degrees centigrade for hydrogen and minus 240 degrees centigrade for helium, Z is less than 1. So, in the previous graph, we have simply related the pressure and the Z. Now, we are simply relating pressure and the Z at various temperatures for one particular gas. I am taking nitrogen. I am measuring the Z for various pressures at a constant temperature. Say, for example, first I take minus 70 degrees centigrade. I maintain that temperature constant. I go on increasing the pressure and measure the Z. It goes down and down and down, and then it goes up, increases. Then I record the same relation for minus 25 degrees centigrade. See, the negative peak slightly goes up. It's going up like this. At 20 degrees centigrade, it goes like this. At 50 degrees centigrade, it is almost ideal behavior, almost, but a slight positive slope. But the Z is not going down at all. It is not becoming less than 1. It is always 1 and greater than 1 at 50 degrees centigrade. So the temperature at which the graph is almost similar to ideal gas is called boil point or boil temperature. This boil temperature for helium is minus 240 degrees centigrade and for hydrogen is minus 165 degrees centigrade. So I stop the meeting. Please rejoin.